So, this is in continuation of our previous lecture. We wanted to discuss the various properties of the continuous functions, and as a consequence of that, we see that if function is continuous over a closed bounded intervals, then we have some results which is known as the boundedness theorem, maximum minimum theorem, and the Bolzano's theorem, and this gives you the also a criteria to find out an approximate solution for the root of the function, that is root location with the help of this. Okay. So, let us see first what is the bounded. Before going for the boundedness theorem, I will recall the definition of a bounded function. Bounded function, we define like this: a function f from a set A to R, where A is a non-subset of R, non-empty subset of R, is said to be bounded on A if there exists a constant m greater than 0, such that the mod of f x is less than or equal to m for all x belongs to m. It means a function is said to be bounded if the corresponding range set is a bounded set. So, when we say the f is not bounded, it means that is so a function f from A to R is not bounded. It means we are unable to get such an m for which this inequality holds, or we can say that if given any m, then a function f is said to be unbounded. Then if given any m greater than 0, there exists a point x which depends on this bound m, point m belongs to A, such that the value of the function at these points will be greater than the desired the given number m. So, whatever the number you choose, you can always find a corresponding a point in A for which the functional value will exceed by that number m. Then we say f is unbounded or is not bounded on the set m. Okay. So, this is we have already discussed. We wanted now the result, the theorem which is known as the boundedness theorem. The theorem says let I be a closed bounded interval, and let f be a function from this closed bounded interval to R, be a continuous function, on I. Then this theorem says f is bounded on I. So, every continuous function on a closed bounded interval will be a bounded function. That is what he says. Proof. We will prove by contradiction. Suppose f is not bounded on I. Suppose f is not bounded on I. So, by definition, we cannot find an m such that the mod of f x is less than or equal to m. So, we can get then for any n belongs to natural number, there is a number x n in the set A such that the value of the function, absolute value of this functional value f of x n will exceed by n. So, corresponding to 1 we get 1 point x 1 in A, so that f x 1 is greater than 1, 2 we get f x 2. So, we get a sequence of the points in A which will satisfy this condition f of x n is greater than n. Okay. But since I is bounded, since I which is giving to be the closed bounded interval is a bounded set, and all these sequences x n which you are getting satisfying the condition say 1, satisfying 1 lies in A, in I, lies in I, because these are all the sequences belonging to I, and I is a bounded set. So, the sequence x n is a bounded sequence, because x n lies between A and B. So, that all the terms of the sequence have a lower bound say A, upper bound say B. It is a bounded sequence, and we know by Bolzano-Weierstrass theorem every bounded sequence has a convergence sequence. So, use the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem so use Bolzano-Weierstrass theorem. This will give, which gives a convergent subsequence x n k of say x n k of this x n, convergent subsequence of x n of x n that converges to the point x, converges to a number x, say x, because by definition x n is a bounded sequence. So, Bolzano-Weierstrass theorem says, by Bolzano-Weierstrass theorem we can get a subsequence which is convergent and converges to a number x. Now, this x obviously belongs to I. Why? Because since x is x n k, all these terms of the sequence x n k lies between A and B. This is a closed interval, I is closed interval, all the terms of the sequence lies between this. So, the limit of this sequence x n cannot exceed between these, will always lie between these two bonds. So, since this is there where I is a closed bounded interval, so the limit point of this sequence x n k over k, this limit point obviously belongs to I, Okay. But this limit point is x. So, this shows that x belongs to I, is it not? So, what we get is that a sequence x n k has a subsequence which is convergent and the limit point belongs to I. Now, f is given to be continuous. Since f is given a continuous function over the interval I, and x is one of the point inside the I. So, this implies f is continuous at x. So, by Henny-Wheeler theorem, therefore, this implies limit of x n k when k tends to infinity is x will give f of x n k, limit of this as k tends to infinity is nothing but what? F of x, okay, because by the convergence part. So, what it shows? This implies the sequence f x n k, this sequence is a convergent sequence, okay, and convergent sequence is always bounded. So, it is bounded. it is bounded, but that gives a contradiction to our result, because this sequence f of x n is greater than n. So, from here from 1, but from 1 what we get? We get mod of f x and k is greater than n of k, which is greater than k, of course, greater than k, and this is true for all k belongs to n, all k belongs to n. So, this continuous function is not bounded on the closed bounded interval. So, this shows that function f, this over this sequence shows supposition that function is not bounded gives a contradiction. So, this gives a contradiction of our second part, but from we get this which contradicts 2, because here this shows this is unbounded, while we have already shown it is bounded. So, it gives a contradiction, and contradiction is because of our assumption that our function f is not bounded on I. So, this shows that function f is bounded on I. This implies f is bounded on I, that is closed interval. So, this proves the result which is known as the boundedness theorem. Now, in the boundedness theorem, we have assumed these conditions. What are the conditions in the boundedness theorem is? First condition is the interval on which the function is defined must be closed and bounded. So, this is one of the condition which we have taken. Second condition which we have shown, the function must be a continuous function on this. So, interval is closed, bounded, and function is continuous, then only we can say f is a bounded function on this. If any one of the condition is relaxed, that is, if we take I to be a simply bounded interval not closed, or simply closed not bounded, or function is not continuous, then our conclusion that f is bounded on I will not cannot be drawn. In fact, we will get a contradiction. We will get the example where we get this function is unbounded when we relax any one of the condition. So, let us see the examples. The condition note, the conditions of the of boundedness theorem. The hypothesis of boundedness theorem is each condition of I is needed to justify or to get the function f, to get a continuous function to be bounded on I. If we relax any one of the condition, then we get the conclusion fails. The conclusion of the theorem fails if any one of the hypotheses or if any one of the conditions of boundedness theorem is relaxed. For example, suppose I take the function, say function f x is suppose x, the interval I am choosing I as an interval is 0 to infinity, okay, and now this function is continuous function, it is a continuous function on this interval I, but I is not that is the function is closed, but unbounded, is not bounded. it is unbounded one, though it is closed, though it is closed, because all the limits point of between 0 1 are inside it. So, I is a closed interval, but it is not bounded. Okay. Then what happens? The function is continuous throughout, but the bound for this function, but function f x equal to x is an unbounded function, because as x increases, the value of the f x keeps on increasing and interval is up to infinity. So, it is without bound. So, it is unbounded, therefore, the conclusion fails. Second, if suppose I take the same function g x as say 1 by x, this function, and the interval I choose I to be the interval say 0 1. Now, this interval is not closed, but bounded. Function f x is continuous over the interval 0 1, because 0 is not included, but we have seen this function is also unbounded, as because as x tends to 0, the function g x will go to infinity, unbounded. Then, so again the relaxing the condition is again not going to help, that conclusion fails. Then, if I take the interval I as a closed interval, which is a closed and bounded, okay, but now I am taking the function h x as 1 by x if x belongs to the interval say 0 1 and 1 if x is 0. I define this function. The function is continuous over the 0 1 interval, okay, but it is discontinuous at the point 0. Clearly, h is discontinuous at x equal to 0. So, again the conditions is not satisfied, and obviously clearly h is unbounded. H is when x approaches to 0, the this is not a bounded function. Okay. 1 by x for this 0 1 and 0 when it is discontinuous and unbounded on C. Okay. So, this will be there. Okay. So, we can see that in boundedness theorem is can only be applicable when all the three conditions are taken in consideration. The next result which we want to maximum minimum theorem. The maximum minimum theorem the theorem says let I be a closed bounded interval, be a closed bounded interval, and let f, which is mapping from I to R, be continuous. On I. Then f has an absolute maxima maximum and an absolute minimum on I. This results. Now, we have already discussed the maximum, absolute maximum and absolute minimum in the last lecture. So, proof we go. What is the absolute maximum? We mean that if suppose a function is from A to R, then f has a absolute maximum at a point if there exists some point x star, such that f x star is greater than f x for all x, and minima when f x lower star is less than equal to f x. So, that is the way we have introduced the maximum of this function. We will discuss after this proof. So, suppose what we want is, suppose a be a closed bounded interval and function is given to be continuous, then it will attain its maximum value as well as minimum value over the interval I. That is, there exists some point where the absolute maximum will be attained, absolute minimum will be attained. So, let us see the problem. So, consider the set f of I, the set of those values f x where x belongs to I, means consider the range set of function f which is defined over I. Now, this range set, the values of f I is clearly bounded subset of R, and this follows from the previous boundedness theorem, because boundedness theorem we have seen, if the I is a closed bounded interval, f is a continuous function, then f of I, then f is a bounded on I, that is the range set will be a bounded set on I. So, it is a bounded subsets of R, this much we. So, once it is bounded subset, we can talk about the upper bound and lower bound and supremum of least upper bound and greatest lower bound. So, let us suppose S star be the upper bound supremum value of the function f I, and S lower star be the infimum value of the function f I. That is, least upper bound of the function f over the interval is suppose S star, and this. Now, what we want to here, this S star and small s star exist. It means there exists some function. What we wanted to prove, required to prove is that there exist points x upper star and x lower star in I, such that the S star will coincide with the f of x star and S lower star will coincide with f of x lower star. This we wanted to show. So, first we will prove for this side, and the other will follow in a similar way. Okay. So, let us assume so first to show that there exists an x star in I, such that S star, which is the supremum value of f I, exists and equal to the value at this point. There exists. This we wanted to show. Okay. Now, since our x star, since S star is the least upper bound of the function f I, of the function f x for x belongs to I. When x belongs to the least upper bound of this function is S star. So, if I choose a number slightly lower than this, it cannot behave as a least upper bound. So, the number S star minus 1 by n, this number is a slightly lower than, so is not an upper bound for it. So, is not an upper bound is not an upper bound for the set A or of the set f I. Is not a bound. Therefore, there exist. So, we can say consequently there exists a number x n in I, such that x star upper minus 1 by n is less than S star, sorry, this is S star minus 1 by n less than f of x n, which is less than or equal to S upper star for all n belongs to capital N, because this is our upper bound. So, when you take a number slightly lower than this, then we can find a some number x n in I. So, that the functional value of x n will exceed by this number, and obviously, it will remain less than equal to this, because it is the least upper bound for this. Okay. Now, this sequence number x n, but this sequence is x n satisfying 1 are lying in the interval I, which is say a b, which is a closed and bounded interval, closed and bounded. So, by Bolzano-Weierstrass theorem, so by Bolzano-Weierstrass theorem, there is a subsequence say x dash, elements are x and say r, belonging to of x, of course of x, x is a sequence x n of x that converges to some number x upper star say. Okay. Now, we want in fact, this number which we have got it must be a point of a b. This we want to show first. So, how to show is, since all the elements of this are again the elements of I. So, since the elements of x dash, that is x and r, these are they belongs to I, which is closed and bounded interval, So, just like a previous thing, we can say, so just like previous theorem, we have seen that if the sequence of the point belongs to a closed and bounded open interval, then limit point will also belongs to it, and since it is closed, so limit point will. So, it follows from this that the limit point x star is also a point in I. Okay. Therefore, f is continuous at I. Therefore, f is continuous at this point also, because it is continuous throughout over the I. So, once it is continuous, so apply the definition, Haney-Van definition. Haney theorem says, if a sequence converges to x star, then f of x n will also converge, x r will also converge to f x star. So, by theorem, limit of f x and r when r tends to infinity coincide with f of x star, because it is continuity. But by the first one, use the first one. From first, what we get is s star minus n r is less than f of x n r, which is less than or equal to s star, is it not? So, this is true for all r belongs to n. Now, let r tends to infinity. So, this limit is s star, this is s star. So, by Eskew's theorem, the limit of this function f x and r as r tends to infinity will be equal to s star, but this limit is nothing but what? F x star. So, this implies there exists an x star belonging to I such that the supremum, because this is the supremum value of the function f I, such that this f x star is the supremum of f of I exists, and that proves the existence of S. Similarly, we can show for that there exists a x lower star in I such that x lower star is the infimum of f of I, and this completes the proof for this much.